So let's continue today's lecture. So for these 2 hours, what we are going to discuss is we're going to discuss these three topics. Okay, sorry, sorry for that. Okay, so what we're going to do is we're going to look at this. Going to look at these three topic interference. Okay, so this is why we do all our modeling based on the distance. Okay? So when it comes to interference, so these are among some of the points here. So we have one and two interference. So there are two types of interference exist in our cellular network, okay, which is the co-channel interference, and then another one is adjacent channel interference. Okay, co-channel interference because we know our cell. Okay, if we allocated one frequency here, then later in some distance, it will be used back. Okay, the same frequency is going to be used back. Okay, if we are the user here, we are communicating with the first in the first cell, then we also can hear. So because our handphones is been tuned to the frequency f1, so meaning that we can also hear the f1 transmission from the other cell. We call it as a co-channel cell. So a co-channel cell. Okay, and because of that, we call it as a co-channel interference. Okay, so the first one is co-channel interference. Okay, so by having interference, it will impact our receive signals. Our receive signal initially is receive signal divided by noise, but now noise plus the power of the interference. Okay, so we are mainly looking at C divided by I. So what we do in our network, normally we assume noise to be very, very small. Okay, very, very small. So we can approximate just to C over I, PR divided by I. Okay, our receive signal divided by the received power from the interference. Okay, so we assume normally the interference power is actually way, way bigger than noise. So we can omit noise. So we just take the significant impact of the resistance of the interference. Then we are working with C over I. So these are the parameter that we use to evaluate our network. Okay, so that will be the co-channel interference. So that's definitely there is a word out there. Interference is the limiting factor for the cellular radio, because now we are computing C over I. So we want our C over I as huge as possible. What does it mean? It means that our carrier power needs to be way, way bigger than our interference power. So that is what it means. So what is also the way we're designing it is actually we want to reduce the interference power. Okay. So it's because of the frequency. So you use F1, co-channel interference. Another one is what we call as that adjacent channel interference. Okay, adjacent channel interference. So adjacent channel interference is due to this our filter. It is all back. So now if we look at adjacent channel interference, we know our spectrum. Okay, so we have F1, F2, F3, F4. So we are dividing our spectrum into frequency, the carrier frequency that we use to transmit the data. And then what we do is we are using filter. If you want to only capture signal at F1, okay, previously we know that we are transmitting using F1. What we do is we are using filter. So our filter is actually only capture frequency F1. So if we put filter, we only get F1. If this is our signal, if we can only get F1 signal, while the rest we're going to remove it because of the filter. Okay, because of the filter. So, however, when it comes to filter, the best filter is square filter. So if you have a square filter, then yes, you only capture the F1. However, filter normally is not ideal. So filter normally is a cosine filter. Okay, filter is the cosine filter. So due to the filtering, some of the power from your neighboring signal, or power from your neighboring signal, which is F2, you will also get it somehow a little bit of F2 because of the filtering. Okay, then this is what we call adjacent channel interference. So an interference because signal that is next to you in the spectrum, in the spectrum. Okay, so the cause of interference coming from your neighboring carrier frequency. So if you're transmitting at F1, normally coming from F2, F3. So depending on how good your filter. So this is one. Another one, adjacent channel interference also due to, remember our small fading. You have F1 over here. You have, let's say this is the second signal F2. And we know that your received signal going to be around your frequency because of Doppler shift. So if the environment is actually moving, sometimes you get lower than F2, sometimes you get higher than F2. Because of the Doppler shift, your frequency is also changing, and plus plus with the imperfect filtering, that is also can cause the adjacent signal to be included in your in your receiver when you try to decode your signal. Okay? So adjacent channel mainly due to filter, because of the filter. Second one is because of the Doppler shift, because frequency, when you transmit F1, you're not going to receive F1. Normally it's F1 plus minus your Doppler effect. Okay, remember that Doppler effect, when a signal touch a moving environment, the reflected one will change in the frequency. Okay, so your delta D depends on how fast the movements of the object, and also the angle where your signal hit the object. Okay, so if it is a static environment, then yes, you transmit F1, you will get F1. But normally, if you transmit F1, you're not getting F1, you're getting around F1. F1 minus delta D or F1 plus delta D, depending on how fast the environment is. Okay, the movements of your of the frequency will also later plus the imperfect filtering will cause the adjacent channel interference. So there are two interference in our network. So these are the two interference. One, because you are sharing the same frequency. That we did. Okay. So one, because you are sharing the frequency using another co-channel. So that is co-channel interference. This is because there are another cell that's sharing the same frequency. Another one is interference because of the next, your neighboring frequency. So this is between F1 and F2, and this is between F1 and F1. Okay? So these are the two types of interference that exists in our cellular network. Okay, so that is the definition. So adjacent channel interference resulting from signal which are adjacent in frequency, to F1, F2. Co-channel is between co-channel cell. You're using the same sets of frequency, F1, F1. Okay, clear? Anything you guys want to add? Okay, so now let's look on the co-channel interference. So this co-channel interference, because of our design, we can actually compute it. We can actually compute it. So the way we compute it is we are using Q, what we call, or D divided by R. This is also called the quality. So you remember D. So D, if your D is bigger, is actually bigger. What does it mean? It means that your co-channel cell is far away from your cell. That means that the interference is less. Okay. So the way we compute co-channel interference is by using Q, D over R. It is also called co-channel reuse ratio. Okay. So if you are actually at this A, you are inside here, and let's say we are computing at the cell H, around there. Okay, around there at the cell H. So cell H, the radius is from the cell H, for user at the cell H, the distance between the user to its tower distance is R, the radius of the hexagon. Another one is your D. Okay, so you can see if carrier divide by interference, you can approximate it again using D. So carrier is what? Is 1 proportional to R. Okay. So your carrier power is inverse proportional to your distance. Your interference power is proportional to D. So that gives you D divided by R. Okay. The more, so you can see at the end, C over I is related to your co-channel reuse. Okay, the reason is your carrier is your PT, GT, GR, and then so on. Let's say we use 4 pi r square. So if you look at it, so C is equivalent to 1 divided by r square, or 1 divided by r n in your path loss exponent. So if it is 2, is a free space loss. If it is 4, is a plain earth. So n can be from 2 to 5, 6, depending on the environment. So if you want to make it more detailed, C over I actually, C over I is 1 over r to the power of n divided by 1 divided by d to the power of n. That gives you d divided by r to the power of n. So it depends on the path loss exponent n. But you can see that it is actually depending on ratio d divided by r. Okay, so co-channel interference, the reason why we only use the distance, because we know if you are coming from the same operator, P is the same, GT is the same, GR is the same, 4 pi is also the constant. So everything you can actually uh, uh, delete when you do C divided by R. So the only thing that is different is the distance. Okay, so at the end, it turns out that your co-channel interference is given by a ratio D divided by R. Okay, let me delete that. Right. Okay, it depends on D divided by R. And we know D divided by R is given by square root 3n. This is when we derive the distance using the area of the hexagon. We know that D divided by R is equivalent to square root 3n. And then if we use R, no, or if we use D equal, no, not, is, back up here, D divided by R equals to square root 3n. Okay, so we know that if we normalize the distance between cell into 1, okay, if we normalize distance between cell, normalize cell distance to 1, what we get is we get radius equal to 1 divided by square root 3. So if you put here d 1 divided by square root 3 equals to 3n, what you get is d equals to square root n. So this is what we have before. Okay. So if you use a normalized distance between cell here is 1, right? If this is 1, you normalize the distance between cell is equal to 1. The radius is 1 divided by square root 3. That gives you the equivalent to square root 7. Okay, but it doesn't really matter. So this is what we derived before. But for the co-channel, then we are using this ratio Q. Okay, where Q is related to the cluster size. It makes sense. You use a bigger cluster, meaning that more cell within one cluster, you push your co-channel cell even further than your cell. Okay, so if n is bigger, that means that d over r is going to be bigger. That will correspond to c over I is going to be better, bigger. Okay, so that is the term used to evaluate our co-channel interference. So co-channel interference at the end is only related to distance. Clear? Okay, so you can see now. So if you plot, we get what what we want is we are computing this D compared to R. Okay, so that is what we do. So based on we can use back the coordinate system. Okay. Another one when it comes to co-channel cell, because if you remember when we derive the number of cluster n, we assume, so the assumptions that we use, is cluster is also hexagon. Okay, cluster is also mainly like hexagon. Okay, so when you assume cluster which is hexagon, what does it mean? Hexagon have 6 sides. It shows that we have 1, 2, 3, 4, 5, 6. So there are 6 co-channel cells around our cell. Okay, because we are approximate our cluster to be hexagon. So in our analysis, we would see that there are 6 co-channel cells around us. This is what we call tier 1, tier 1, tier 1 co-channel cell. Okay, tier 1 co-channel cell. Of course, there will be more tier 2, okay, around it. Okay, but if you consider tier 2, this is like Fresnel zone. You do normally you only consider tier 1. Tier 2 meaning that the distance is actually double of tier 1. Tier 3 is triple. So we assume because of the distance becoming bigger and bigger, so the value of interference that coming from tier 2, tier 3, tier 4 is we can omit it. So we consider mainly the tier 1. Okay. So here the point that I want to make, is doesn't really matter what cluster you use. For example, this is cluster 7. There are 6 co-channel interference. So if you are using cluster 4, if you're using 4 cluster, meaning that 4 cell per cluster, again, there are 6. So when we do analysis, we still see there are 6 co-channel around a cluster 4. Okay, there are still 6 co-channel around it. Ada satu lagi kat sini. Okay, there are 6. Because of why? Because we approximate our cluster to be hexagon. Okay, so it doesn't really matter what number cluster. We will assume there are 6 around us that is going to impact our cell. Okay, so this is important because of why? Because if you want to do power received divided by power interference, if you look back over here, it must be power received plus 6 power I. Okay, there are 6 coming in. So first coming in, second coming in, third coming in, fourth coming in. Okay. Okay, so your interference power is actually 6 because they are coming from 6 cells. Okay, so this is actually approximate. So the approximation is around 1 divided by 6 D divided by R. Okay, there are about there is about 6 power 6 co-channel that is going to impact our cell. Okay. Okay, so please remember the 6, right? What the reason why it is 6? Because when we derive the cluster size, we approximate it to be hexagon. So it doesn't really matter 4, 7, 3, 12, 19. We assume there are 6 around us. Okay, so the equations for to compute the C over I is D divided by R. So you can see here what would we, so let's look on the example. What would be the minimum distance between the center of the two cells with the same band? So what does it mean? It means that you want to compute the minimum distance between the two co-channel D. Okay, this is what you want to get. Okay, between the two co-channel. And they said the radius is 1 kilometer. Okay, then we know so we can just straight away use the equation. So if you have the reuse factor, so n is equals to 12. Okay, so this is, what does it mean? It means that a cluster with a 12 cell. Then you can plug in all the value, you get the distance over here. If this is 1, this is actually 6. 6 kilometers. So so approximately we can say that it is actually around 6 times. So the received power is actually 6 times bigger than the interference power. Okay. Okay, so another way to, okay, so now let's look on another example. If you are being given this kinds of topology, okay, you have your user here. This is yourself. This is your co-channel. Okay, this is your co-channel. And you can see that this what the number that you need to get is, this is for 1G, this is for 2G. So this is actually an old system, okay? 1G and 2G. So we don't have the information for 3G, 4G, and 5G. So analog system, you can see requirement for the analog system to work, you require higher dB, of course. Then when you change the analog to digital, you can have digital to work by only having a lesser C over I. Okay, so there is at least like 7 dB improvement. Okay, 7 dB improvement. Okay, so in here, okay, so if you want C over I, let's try to evaluate this configuration. How can we get the C over I? So if let's say our mobile system is actually a cell border, what we can do is we can see C over I is given by what? Is given by, so you can see this is actually the distance, 1 over R to the power of n. Okay, to the power of n. Why is it n? Because n is the pass loss exponent. So if you assume it to be free space, n equals to 2. Okay, so your carrier power is inversely proportional to R. So what is your interference power? 1 divided by D minus R. So if you already have the topology like this, then we know we don't use D anymore. This is actually D divided by R, because D is the distance from cell to cell. You want to compute something at the cell border, and we look at, and we have some the arrangement to be in a straight line, then the distance between the co-channel cell to your mobile station is D divided by R. Then you can play around with it. So D divided by R divided by R to the power of n. And that gives you D divided by R minus 1. Okay, so your C over I is nothing else, is your Q minus 1 to the power of n. Okay, so you can see here you will get, okay, So if we say n equals to 4, okay, let's take power 4. And we have here d divided by r minus 1 to the power of 4. Okay? D divided by r is what? D divided by r is equals to square root 3n. So here, cluster size, do we use the cluster size? Okay, we assume, so for this example, we assume you're using a cluster size of 7. So it's a square root 20. 7 times 3 is 21. That gives you about 4.58. Okay, so that is why if you put here 4.58 minus 1 to the power of 4, that gives you 3 to the power of 3.58 to the power of 4. Then you get a value, and then you take the 10 log of it, you get the 22.16 dB. Okay. So if there is only one co-channel cell, our C over I with the cluster size of 7 is around 22.16. What does it mean? It means that it can be used for digital, it can be used for cellular. Your cellular and your cellular for analog and for digital. So analog is require minimum at least 18. Digital is 11. If you only have one co-channel, you get around 22. So it is actually higher, bigger C over I. So this value can be used for both analog and digital. So that is why normally we are using cluster 7. And this is only considering one co-channel. Yeah. Later we have to consider until 6. Okay. So if you can take your calculator, can you convert 3.58 to the power of 4 into dB? Make sure that you get that 22.16. Everyone can get it? 3.58 to the power of 4. How to get that 3.58? Okay, thank you. Okay. So at the end, it goes back to D over R, because C over I, when you want to compute C over I, it will always be you need to use the distance. So for carrier, the distance is your radius. Then radius with the power of is either n or alpha, the Pascal's exponent. It varies from 2 to 6. Depending on the environment. If it is urban, it can go like 3.5. 2 is free space loss. Okay? So we put it n like that. And then for the interference is 1 divided by. So in this case, the distance is not d, but the distance is d minus r, because we already have a topology where we can straight away compute if the mobile station is actually in a straight line. Okay, so in here, what they're trying to do is, so they have a topology that the mobile station is in the straight line between the two tower. So now meaning that we can have straight away this is R and this is D minus R. Okay? And because of that, we can know C over I is 1 divided by R and divided by, what is that? Is 1 divided by D minus R n. Then you have to do the mathematics. So D go up, D minus R, and divided by Rn. Then we get D divided by R minus 1 to the power of. Okay, so at the end, it goes back to D divided by R. So if you want to write also here, this is Q minus 1 divided by N. So the quality of, or the reuse factor Q, where we know our Q, I write it here, Q is given by, is also related to the cluster. Okay, cluster 3N. Okay, so that's why we have at the end, if we assume we use a cluster 7, and cluster 7 meaning 3 times 7, which is 21, you get 4.5. I always like to do C over I, Q minus 1 power of N. That's why we have here 4.58 minus 1. It doesn't really matter how you want to do it, but at the end you get 3.58 to the power of N. And we use N equals to 4. Then you get the answer in linear, then you have to change into dB. Okay, so if you only consider one co-channel, then cluster 7 is sufficient to achieve the two minimum C over I. Analog, which is 18, and also 11. Because one co-channel gives you around 22.16. Okay. Now, so this is another example. So you can say, so if the example gives you everything, they give you frequency, GT, PT, R. So the main reason over here is it only depends on D. Because of why? Because our PT is, let's say we take it PT, PR. We receive is PT, GT, GR, then for pi, let's say we put R, or distance to the power of N. Okay, so this is, so if you look at C divided by R, so you can get PT, GT, GR, GR. 4 pi R square divided by PT, GT, GR, 4 pi D minus R square. If let's say we use 2, then we can know everything's are cancelled each other. So it turns out it get you 1 divided by R2, 1 divided by D minus R2. I use 2 here because this is a simple example for free space loss. So at the end, it only depends on the distance. So you can rearrange back, you get the answer. So instead of using 2, I'm using N to make it generalized. Okay? So how does the received signal attenuate based on the distance? Depending on the path loss exponent. The bigger the path loss exponent, what does it mean? It means that it attenuates further. It attenuates faster. It's not further, faster. Okay? You just move a little bit, the signal drop really drop in with a significant amount. Okay, if your N is bigger. So at the end, when you want to compute C over I, you don't need frequency, you don't need GT, you don't need all of that. What you need is just the ratio between D and R. Okay, because we can see C divided by R, all the frequency, all the GT, all the PT is going to cancel each other, because we assume they're coming from the same vendor, from the same operator. So all the equipment used in both co-channel cell is the same. Now the only thing matter is the distance. Okay, clear, right? Okay, so at the end, this is the generalized equation if you have only one cell. Okay, so if you want to simplify that, it's even further like D divided by R, which I really like to do that way. So that is the answer. But what I want is I want to have D divided by R minus 1. I always like to have this equation. Okay? Then you can put lah D is 5, R is 1, minus 1 to the power of N, then dapat 4. Okay, so it turns out that so here once we remember if we put in our coordinate, our R is 1 divided by x square root 3. So when we go into a real application, then R you have a value lah. Okay, when you have a value, then D divided by R, you also get the value for your D. Yeah? Okay, so that is how you evaluate co-channel interference. Okay, so what we have done now is to how to the idea on how to evaluate the co-channel interference from one cell. Okay, from one cell. Okay, so at the end, the idea is it depends on this value, which is D divided by R 3n square root. Okay. So if n equals to 3, so 3 times 3 is 9, square root 9, that's why you get 3. Okay. If n equals to 7, that's cluster 7, just now we get 4.56. 6 and 6.2. Okay, depending on the size of the cluster. So it depends on Q. So Q is the one telling you about the co-channel interference. So the one over here is the same thing. Small q, meaning that cluster size small. When you have cluster size small, you can have more frequency in one cell, meaning that larger capacity per cell. But small cell separation D is small, your CCI is going to be small, okay? Because your co-channel is nearer to you. That will reduce the voice quality, and this is not so great for user. This is not good for user, but good for the operator, because you can have more user. Okay, so that is how you compute or you evaluate the C over I, the co-channel interference. It has to go into distance. Okay, so now let's look on the entire network. When you have 6 co-channel around you. Okay, when you have 6 co-channel around you. Previously, we only consider 1. Okay, then the idea is simple. It's just that you need to add all the interference. Okay, you need to add all the interference. Okay, so that is how you compute the signal to interference ratio when you have 6 co-channel around you. Because all these 6 will actually interfere to your cell. Okay? So let's look on this. So if you look at 6, okay, 6, so we do remember this is 1 divided by r. Okay, 1 divided by r. So your signal is inversely proportional to your distance. Or if you want to write Rn, so R negative N. This is what you do. Okay. So if you approximate, so this is the approximation. Yeah? So you approximate your signal power is depending on your distance. Your interference power is depending on the on D. So 1 divided by R, another one is D. Okay. 1D, 1 R. So if you look back over here, if you want to simplify that, this is get you R divided by negative N If you add, okay, you add from 1 to I naught. 1 to I naught. What does it mean? It means that you get D, negative N, I naught. Okay, right? If I naught is 6, so in this case it's 6 lah, 1 until 6. Then if you want to get, you get R negative N, 6, D negative N. 6, because there are 6 interference coming in. Then you get here 1 over 6. Again, you get D divided by R. Okay, that will be your signal to interference ratio. Pada pula, ni 6, sorry. 6. Okay. So you have from here to here. So if you look on the next page, then you have this. How many co-channel cells around you? So in this case, in our case, normally we take 6. Okay, there are 6 co-channel around our cell because we approximate our cluster to be also be hexagon. Okay. Then you have, if you get back, so these are the equation for the co-channel interference for the entire network. Okay, for the entire network. So it depends on D divided by R and then 1 divided by how many interference. Okay, if we consider the previous one, the 1 divided by 6. Okay. 6. So then D divided by R and also equals to Q. Q is related to your cluster size. Okay, cluster size. Okay, so there are nothing new over there. Okay, so you can see for the entire network, it depends on how many co-channel cells around you. Okay, I naught. So for example, if I have this cell, normally we have 6 cells around us, but in the drawing, I only have 4. Why? Because this area around here maybe is a mountain. So there is mountain, there are no people, then there are no base station. So if this is the case, if this is how it is been drawn, then I ask you to compute your S over I, then I naught equals to 4. Okay, so depending on the topology, So if it is a plain one, you have 6 around you, then you need to have 6. But if they are there for the previous example, this side is actually mountain. So there are no cell over here. There is only have 4 around you. Okay, so then you have 4. Okay, so the number of interference depending on the topology. In general, if it is a full scale network where a co-channel interference is actually around you 360, then you have 6. Okay, you will have 6. This is how you compute you approximate the you compute the C over I. Any question on this? Yeah. Okay. So then we also have what we call as worst case co-channel. Okay. Previous one, the one that we approximate D divided by R divided by 1 divided by 6 to C over I, because we just assume it to be user to be around the cell. But if we assume user to be at the cell border, if we assume the user be at the cell border, then there are different D. Okay, if you assume to be here, then you can see that from co-channel 1 and 2, the distance is D minus R because it is actually nearer. Okay, for 3 and 4, the distance is D. But for the 5 and 6, where co-channel coming from the back, the distance is D plus R. So now if you need to get your S over I, you have to use a different one. So you can have 1 divided by Rn. First one is 1 divided by D plus R, and how many times? 2 times, plus 2 times dn plus 2 times d plus r. Okay, you have 6. Okay, you still have 6 interference, but 2 of the co-channel, the distance is d minus r. 2 will be d, and another 2 will be plus d plus r. Okay, so if you look back over here, you have something like that. So 2 d minus r, 2 for d, and 2 for d plus r. Then you can actually change it. Means how do you change it? Rather than I put d up, I put r coming down. So you can see here, if you have 1 divided by 2 d minus r negative n divided by r negative n. Okay. So instead of I put it up, I'm bring it down, because I know the denominator now has 3 components. So I cannot take the denominator going up. So what I can do is, just since I only have 1 component for my in the numerator, then I can bring that Rn go down. Okay. So when I bring it go down, then I can get the value negative n. So here is actually what? 2 d minus r to the power of negative n, just now divide by r negative n. Then you have to plus 2d negative n divided by r negative n plus 2d plus r and divided by r negative n. So everything here is 1 divided by that. Then you can do lah. So d divided by r minus 1 negative n, 2. And that will give you 2 q minus 1 negative n, which is this one over here. Okay, 2q minus 1 negative n, 2q negative n, and 2q plus n. Okay, so you can see here, this is a worst case scenario. So worst case scenario, you have 3 different components of distance. 1, 2, 3. Okay, 3 different component of distance, because it comes from 3 groups. Okay, 1 and 2, the distance is approximately to be d minus r. 4 and 3, 3 and 4, d, well, the co-channel at the back is d plus r. Okay, so you cannot approximate to have d divided by r anymore. 6. Okay, your first focus for this, you approximate all 6, the distance is d. But for the worst case scenario, when worst case scenario happen when the user at the cell H, then there are 3 types of distance coming from the co-channel. 2, which is d plus r, coming from the back co-channel. By the side is d, by the one in front is d minus r. Okay, by having three different distance, then you can have 3 groups of q. Okay, so if you consider n equals to 7, again, q just now, q equals to 3n square root 3 times 7 square root 21 is about 4.58. In this case, be approximately 4.6. Okay, so if you put 4.6, if you consider all of this, n equals to 4 into this equation, you can get C over I is about 17 dB. 17 dB. So you can see here 17 dB. If you consider worst case scenario, 7, you cannot use 7 cluster for the analog system. For 1G, you cannot use 7 cluster. You have to use bigger. Okay, you have to use bigger, but you can use for digital, which is GSM. It's GSM only 11. So I will give about 2 minutes. Can you please compute that 17 dB? Please compute that 17 dB. Please make sure that everyone can get this value. Got it? Got it?
Yes, Doctor.
Got that? Good. Okay, so you should get that 17 dB. Okay, 17 dB. So if you're using a cluster of 7, you are not able to use it for analog system, because analog system you need at least 18. So if you want to use for analog system, then you cannot use cluster 7, but you have to use a bigger cluster. For example, n equals to 12. So if n equals to 12, what does it mean? It means that 3n. So 12 meaning that 3n 12, 3 times 12. That will give you 6. Okay, so your d over r is equals to 6. Okay, so then you will have bigger than 17 dB. So your this is equals to q. Okay, so your instead of using q4, you use q6. And then definitely if q is 4.6 is 17 dB, q6 is going to be a bigger 17 dB. Okay? So if you cannot meet the requirements of your C over I, the only options you have is you need to use a bigger cluster. What does bigger cluster mean? Bigger cluster means that you are pushing your co-channel cell further away than you. Okay, so if this is your cell, your number 6 over here is going to be further away. Because of why? Because the size of the cluster is bigger. Okay, the size of the cluster that you use is actually bigger. You are pushing the interference channel away. And because of that, it improves your C over I. So for the worst case scenario, so that is why for GSM, our 2G, the most popular cluster size is 7. Popular cluster size is 7. So they are using 7. How about if they are using 4? So this is homework, eh? I would say you can try. So Q sir. So try to use cluster size n equals to 4. What will be the C over I? Okay, so you have to compute your Q first. 3 divided by 4. 3 times 4, what? Square root 12. That will be your Q. Then instead of 4.6, you use square root 12, then you will get your C over I. Okay, so C over I is going to be smaller because you are using a cluster that is smaller than 7. It should be smaller than 17 dB. Okay, so that is normally how you compute C over I. Okay, the best one is to compute C over I for the worst case scenario. So worst case scenario and is when the user is actually at the border. So you can actually check C over I is 17 dB, and if you're using this, it's actually higher than 17 dB. Okay, because this is not the worst case scenario. This is just the approximation that all co-channel have the same distance D. So when we consider worst case scenario, then we have three groups of distance: D minus R, D, and D plus R. Okay. Okay, so let's look on the example. Let's look on one of the another example. If a signal to interference ratio is 15 dB, so you require 15 dB. So a system requires 15 dB. What is the frequency reuse factor and the cluster size that should be used for maximum capacity? So when you say maximum capacity, what does it mean? It means that the smallest cluster size. Smallest cluster size that give you C over I bigger than 15 dB. Okay, the smallest cluster size meaning that you can have the per one cluster you have more frequency inside. Okay, so you need to find what is the smallest cluster size that can give at the C over I bigger than 15 dB because you are required to have a network at 15 dB. Okay, and then they say here assume there are 6 co-channel cell in the first tier 6 lah. Use suitable approximation. So now they are using at 2 different environments. So one is n equals to 4, one is n equals to 3. A meaning that is a more severe environment because your attenuation is going to be faster. Okay, so question A. So when you look at n equals to 4, okay, so they are trying to using a D over R of 7. Okay, so they say first let us consider 7. The 7 cluster size D over R just now equals to square root 3n square root 21. So that is 4.58 or 4.6. Okay, if you use the approximation one, the on average is 1 over 6. Okay, 4.58 to the power of 4 divided by 6. Okay, so this is not the worst case scenario. You will get around 18.66 dB. Okay, so they are using this. So 18.66 dB meaning that you can use cluster 7 when n is equal to 4 because you are required to at least have it 15. So when you do 7, it should be bigger than 15. So what does it mean? It means that you can use 7. Okay, you can use 7. But you can use 7. But this actually did not answer the question yet. Smallest cluster size. So 7 meaning that 7 can be used. But how about 4? Because that will be a smaller. You also need to check 4. So please do also with cluster 4 and see what is the C divided by I. If cluster 4C divided by I is bigger than 15, meaning that you have to use cluster of 4. Okay, because you want the maximum capacity. So if for this one over here, you can only use it just shows that you can use cluster 7. So if let's say let's go and try to look at 4, cluster 4, okay, n equals to 4. So that is the the next smallest cluster before after 7. Then you get 3n q 12. So can you try to get the s over I? So s over I is equal to 1 over 6 square root 12 to the power of 4. Yeah. Yeah. So I get around 13.8 dB. So can everyone get the same answer, 13.8 dB? So meaning that I cannot use cluster 4. So then it means that it is correct. You need to use the smallest cluster will be 7. Did everyone get 13.8? If I'm using cluster 4, okay, yeah. So if I use a smaller cluster which is 4, my C over I is 13.8, which is meaning that it does not meet the requirement of 15 dB. Okay? So I have to use a bigger cluster. I have to push away the co-channel cell even further. So the next bigger after 4 is 7. So that's why over here it shows that 7 is sufficient. 7 can achieve 18.66. Okay, so this is for 4. Now let's look at n equals to 3. They still use 7. And it turns out that it only achieved 12.05 dB. Okay, everything's are all the same except for n equals to 3. Okay, n equals to 3. What does it mean? It means that this is a better environment. This is a better environment. So for a interference limited system, it turns out that the pulse loss exponent play a very crucial component. Okay, because of why? Because we know our our cell, right? There are 6 around. There are 6 around our cell. The interference that coming in, if n is bigger, what does it mean? It means that the power of interference is going to be lower. So less interference will come if the environment is severe. So it turns out that in a very complex environment, the interference that comes to our co-channel to our cell is less, because when interference needs to propagate from the co-channel cell towards your cell, it is going to be attenuated severely. Okay, so that is why if you have a worse environment, n equals to 4, somehow your co-channel interference is bigger. Once the channel becoming better, n equals to 3, your co-channel is going to be your co-channel. Your C over I or S over I is going to be lower. What does it mean? It means that the interference start to disturb you because the environment is better. Interference can propagate from far away to you without being attenuated severely. So a pulse loss exponent is actually a friend. Is going to help your interference limited signal if the environment is becoming more complex. Okay, so this is also among a part of it that you can use when you do your assignment. So when you decide, if you start with n over 3, you cannot fulfill the requirement 15 dB. One way is you can use n equals to 4, but you have to justify with the area that you choose. So if you use area highway, because remember the assignment said just a city, you can choose any, you can use any location. So if you want a location that have n bigger, it's going to be your friend. It is going to help the C over I. So it has to map nicely with the environment. Okay, so you cannot just say you are doing in highway, but you assume that your n is equals to 4. So highway is not n equals to 4. N equals to 4 is in the city area. Okay, so in here, n equals to 4 is in the city area. So it turns out that when the environment is complex, the interference that want to disturb you is also going to be attenuated first severely before it reach you. Okay, before it can reach you, it is already attenuated severely because n is very very bad. So n high is actually a friend in a interference limited signal. Okay, so this is the key point here. So you can see if n equals to 3, everything's are the same, you cannot meet the requirement of 15 dB. So what's to do next? You have to push the co-channel even further. How to push even further? You need to use a larger. So use larger n equals to 12. You can see 12 over here. It's just simply above your requirement at around 0.56. So this your requirement is 15 dB, right? This one 15 dB. So if you're using 12, you can at least just above the requirement. So you can say for n equals to 3, you cannot use 7 cell reuse pattern, but you have to use 12 reuse pattern. So you want once you use 12, what does it mean? It means that the number of channel per cell is going to be lower. Okay? So if you compare, if you have 7, and if you compare, if you have 12, 12 lah. Okay. Okay, so number of frequency per cell is going to reduce. Okay, remember number of frequency per cell is the one that you use for the trunking. So the bigger the number of frequency per cell, when you use trunking, you have more traffic intensity. Okay, so this is how this. So for this example, it shows that n equals to 4 is going to help you when you deal with interference. The reason why, the reason is your co-channel, when they want to disturb you, the signal is already attenuated severely because your n is big. So your PI is going to suffer. Okay, your PI is going to suffer. So when you reach you in the cell, it's going to be very very small because he has to travel at the longer distance, and at the longer distance your n is big, it will be attenuated really really fast. So the one reach your cell is going to be very small. That improve your C over I. Okay, so n play a very crucial thing in the interference limited system. Okay, so now next, so that is co-channel interference. So co-channel interference there are two. One is the average one, we just divide by 6. Another one is the worst case scenario. Here, worst case scenario. So two equation. 1, 2. Okay. Then depending on the questions, you should be able to compute the C over I. So then depending on what is the requirement needed, you should be able to tell what is the smallest cluster size that you have to use in order for you to have the maximum capacity. Okay. Another key is path loss exponent play crucial thing in the interference limited system. The bigger the path loss exponent, It means that the interference is going to be attenuated even more. And the one that reach you in your own cell is going to be very, very small. And that's improved S over I. So next we look at adjacent channel interference. Adjacent channel interference. So what does it mean? This is between F1 and 2. You do so once you put filter, you don't want the F2 to go in. So this is the adjacent channel interference. So interference from channel that is adjacent in frequency. The primary reason for that is imperfect receive filter. Okay, refer that receive filter. Okay, never mind. Mobile in the same cell. Okay, so the main problem is when you have a same cell. This is you as the user, and another user is using F2, F1. Communicate, right? Or when you transmit. So meaning that there are someone using F2 next to you. Then this that the signal power from the other user may come to you, may also get some of its signal because of the imperfect filter. So if this is the case, then the way we deal with it is very simple. It's just channel allocation. Later we'll see. So this is the main reason. Perfect channel, perfect filter versus imperfect filter. So the one next to you is called. You will also uh, filter up some of the signal from your adjacent channel. Okay. Uh, Main reason, local oscillator drift. If your frequency that you multiply is also there is a shifted, meaning that some error in the electronics can also provide that Doppler shift. This is environment. Okay. Right. So for the environment, your transmit frequency when you receive it, it may change a bit because of the Doppler shift. Okay. So the main thing over here, if you want, so okay, let's say we look at the cell cluster 7. So the approach that we use to solve adjacent channel interference is simple. So we don't want to use the adjacent channel in the same cell. So for example, if this is frequency 1, we use here. Frequency 2, we don't want it to be in the same cell. We have to put frequency 2 over here. Frequency 3, frequency 4, 5, 6, 7. Then frequency 8, 9, 10, 11, 12, 13, 14, and so on. Okay. So this is normally how we deal with adjacent channel interference. So if we look at it from the spectrum point of view, if this is frequency 1, then we only use frequency 8 in the same cell. So the rest of it over here, we are not using it in the same cell. So if, for example, cell number 1 here, this is cell 1. What the frequency that the frequency that we use is frequency 1, frequency 8, frequency 15. What does it mean? It means that we have a gut band. We make the gut band as big as possible. So that is normally how we deal with adjacent channel interference. We don't use our adjacent channel in the same cell. Okay, so because then if this is happening, our next user in the same cell is going to use slot number 8. So if you have an imperfect filter, normally you will not get from the frequency 8 because it is actually far away. The gut band is bigger. So that is normally how we avoid ACI. Okay. While for co-channel interference, the way we avoid or the way we reduce, we cannot avoid for co-channel because it's already been there. The way we improve it is by having a bigger cluster. But for the adjacent channel, the way we do that is we don't use our adjacent channel in the same cell. That is the approach that we use. So that we we increase the gut band. Okay. So at the end, it looks something like this. So cell 1, we have only 1, 8, 15, 22, and so on. Okay. So if you look from the spectrum point of view, you have 809.1 simple frequency, then you have 891.5, then so on. Okay, you do have some sort of a gap. Okay, we call frequency gap of the gut, the the gut band. Okay, so this is the approach that we use to reduce adjacent channel interference. Okay, so it looks something like this. So this is a cluster of 7. Here, this is a cluster of 7. Okay, that will be the cluster of 7. So the frequency slot that we use is not going to be next to the adjacent channel is not going to be exist in one cell. Then another one is we can also use cluster sectors. We call it sector. One cell. Later we'll see how this approach can use to improve COI. When we have our tower, we can transmit 360 direction. So this is what we call omni. We use omnidirectional antenna to cover 360. Another approach is what we can do is we make sure they use directional. So we divide our cluster, our cell into 3 sectors. Then every sector we have 1 antenna to cover the sector. So okay, so to cover the sector. So the way we then when you do that, the way you allocate the frequency, you can push it even further. Okay, you can see for sector 1A, 1, 2, 3, 4, 5, 6, 7. Then sector B is 8. What does it mean? It means that within one sector, there you are having, so previously is 1 and 8 within one cell. But now 1, 8, and then now is one sector is 1 and 22. You make your gut band even bigger. If you divide it into sector, then one sector, the adjacent channel is actually bigger. The range, the gut band between the 2 adjacent channel is going to be bigger. So sectorized cell will have better performance in the adjacent channel interference. The way they allocate is you have to rearrange this way. You have to rearrange based on the sector. Based on the sector, yeah, sector 1A, 2A, 3A, 4A, 5A, 6A, 7A. After 7A, then it goes to 1B, 2B, 3B. So you have to rearrange it this way, and then you just allocate it 1, 2, 3, 4, 5, 6, 7 until 21, and then repeat back. So at the end, it turns out that the gap between one sector is bigger. 1, 22, 43. You see, if you don't use sector, gap is smaller. 1, 8, 2. Okay. So by using sectorized, you can even push your adjacent channel away further. Okay. By allocating the frequency based on accordingly using this approach. Okay. So for adjacent channel interference, the problem is because of the imperfect filtering, you may have some drifting in your local oscillator. If your local oscillator frequency is slightly changed, when you multiply it with the signal, it will go your IF, your intermittent frequency is going to be different, and that will also contribute to the imperfect or to the addings of your adjacent channel into your filter. Okay, and then another one that of course because of the environment. So how to deal with it? You have to put a guard band. In our cellular network, guard band can be easily introduced by allocating the frequency using this algorithm. So you have to make sure that the adjacent channel is not going to be available in the same cell. Okay? Yeah. Okay, so when it comes to cell, then I think this is just some words. So when cell, normally we use hexagon. So it become triangle when we use sector. It looks like a is we can use when we use sector, it turns out that it can go to the shapes of triangle. So this is example sector of 6. Okay, meaning that every sector will have one antenna covering the angle. Okay, so when it comes to cell, the normal regular one is hexagon. Once you start to have the sectorized, it can change into different shapes. Okay. The types of cell, you have a smaller one inside building, we call picocell, until macro mainly in the highway. Okay. Yeah, they have their distance lah. The distance. Okay. So depends. So in size. So there are a lot of there are a few types of of cell. Okay, the one that we've been using before are omnidirectional cell, meaning that one cell we cover 360. Now let's look on sectorized cell. Let's say we divide into 3 sectorized cell. So if you divide into 3, what can you do is you can reduce the power and just use 1/3 of the power because you only need to cover 1/3 of the area. Plus, it is a directional antenna. You can control the gain. That will give you better penetration. So directed antenna can have you can change the gain, and normally it can penetrate building better. So this is another advantages when you divide your cell into sector now. Okay, previously you can push away your adjacent channel. Then another one, by having directional antenna, you can have a better can have a better coverage. This is what we want to see. We can also have a better interference. Our C over I is going to improve. Let's see how. Okay. So when it comes to sectorized, there are two types. So there are 3 sectors where your hexagon is divided into 3, 1, 2, 3, or 6 sectors. You divide into 6. So the tower is just the tower. Instead of one antenna covering, you need to have 3 sides. And at the back satu lagi. With these 3 lah. Okay. So if you look at the antenna, if you already have a chance to look at the tower, normally there are 3. Or sometimes if there is a building, if there is a building, There is a building. If you can see, if you notice some building, because they don't have antenna, what they do is they put antenna one here, one at the back. Again, so this is looks like they use the building as the tower. This will cover one sector, one sector, one sector. Okay, so if you have a tower, you can see normally they have three sides. So all our practical system now we have three. The three square one. Three square one. So if you have tower three square one, and then at on top of it there is the circle one. Okay, the circle one is your backhaul link. What does it mean? It means that you have a tower, one, two, three to cover sectorize, and this is the backhaul link. Backhaul link to connect the two tower. So the best connection between tower is you use fiber optic. But sometimes in the area that you cannot have tower and tower to be connected with fiber optic, that is why you use microwave link. So that is been given by the circle antenna on top of it. The square long one is for the sectorized. You have three. Normally, if you look at the tower, there are three. On top of it, there are a circle one. If there is a circle antenna, meaning that there are no fiber optic. So, okay, there are no fiber optic connecting to the tower. So they have to connect the tower to tower by using another wireless link. So this is actually the sectorized. Okay, you can divide you can divide the hexagon into 3 and into 6. So what are the advantages? So the advantages is actually the C over I, S over I. Okay, if you look back over here, so this is mainly our cell. This is actually our cell. Initially, if every tower transmit 360, we will receive 6 interference. But if it is sector, if this is actually sector, so we instead of having 6 interference, it will reduce to only 2 interference. Because of because of why? This sector, so you're using the same frequency here, right? F1. This is also F1, but this F1 is transmitting this way. You will not interfere to your sector anymore. So meaning that, what does it mean? It means that this sector is not going to interfere you. This sector is not going to interfere you anymore. This sector is not going to interfere you anymore. So here clearly 3 sector is not going to interfere you anymore. But okay, 3. And if you look back over here, this sector is also not going to interfere you, because this is the line. You're going to go outward this way. Okay, so 4 co-channel cell will not interfere you anymore. As a result, your S over I, instead of 1 over 6, is only become 1 over D by R squared. It reduces to only 2 cells, which is this 1 from the back. Okay, so by having sectorized, then 4 of the co-channel cell is not going to interfere with you anymore. Only 2 at the back is still going to interfere you. That improves significantly your S over I. Remember S over I? If you look back, S over I here, I naught. So initially we use 6. So now it's only 2. Okay, so there are an improvements of C over I, or S over I. Okay, and because of that, you can see previously C over I is 17 dB. If you're using sectorize of 120, meaning that it's only two, okay, you only have two co-channel interference. Your C over I improved to around 24 dB. Okay, around 24 dB. Okay, so please try to get this 24 dB. So you can use a few approach. So the value is around 24 to 29, depending on how you define your distance. For example, if you want to compute over here, okay, so the distance is actually D plus R. Okay, if you consider D plus R, then you get 1 divided by R and 2 1 divided by D plus Rn. D over I. Okay, you get something like that. Okay, or if you only want to see not D plus R, so C over I can be this, or C over I can also be, if you consider this as D, approximate it to be D only, then 1 over 2 D divided by R to the power of N. Okay, so you have two values. So one is +1, one is without +1. So this, please try to do it, and you get around 24 to 28, if I'm not mistaken. Okay? So you'll be around that with the cluster size of 7. The things over here is it improved from 17 dB to more than 24 dB. So that is what it means. Okay, so that is what it means. So this, if you're using 120 sectoring. If you're using 60 degree, 60 degree. So previously is 120. Okay, this is 120 degree, 120 degree, 120 degree. So if you're using 60 degree, meaning that you divide your cell into 6. Okay, only 60 degree. Okay, so for example, so in this case, it's only that part. Okay, it's only this part. Then this is going to be this part. This is going to be this part. So it turns out that you also going to exclude this. So it's only going to be disturbed by one only. So only one co-channel cell is going to destroy impact your performance, because the one over here, if you only consider this, you will not overlap with your cell anymore. So this is what it means over here. So two co-channel, if you're using 120, if you're using 60, it's only one co-channel cell. Okay, you can see from the diagram. Okay, 120, this and this. Rest are all no. If you consider smaller one, then this one no more anymore. It's only this one over here. Only one co-channel is going to interfere with you. Okay? So by using sectoring, you are actually improving your C over I. From a dB point of view, you're changing from 2 to 1. This is actually double, right? You get, if you have improvement of double in dB, will give you 3 dB improvement. So if it is 24, 460 to 120 sectoring, then it will go 27 dB. C over I, if you are using 60 degree sectoring. Okay, 60 degree sectoring, you will get improvement another 3 dB. So this is also what you can use when you design your network later. If you want to use sector, you decide first in your network sector. You have to compute your C over I. So based on the C over I over here, now it's 24 dB. What you can do is, instead of using seven cluster of 7, maybe you can use cluster of 4. If you're using cluster of 4, maybe you get around 17 dB. That's still going to be, it's still going to work with that, with the requirement 15 dB. So by improving the C over I at the higher cluster, so what does it mean? It means that you can use a smaller cluster size if you want to add the number of user per cell. Okay? So during your design, what you have to do is you have to decide whether you want to use a sector or not. If you want to use sector, you have to compute C over I based on that sector. It's either sector 100, 120 or 60. Once you have that, you should be able to decide which N you want to use. And with a better C over I, you can use a smaller N. Using a smaller N, you have a higher number of frequency per cell. Higher number of frequency per cell, meaning that your trunking intensity is going to be bigger. Then you can boost up the number of user per cell even bigger, because you have a bigger, you start with a bigger number of physical channel. Okay, so these are all methods that you can use to improve the number of user per cell. Okay, so how is the capacity increase? Sectoring improves C over I. Okay, when you have better C over I, if it is already over the requirement of your system, what you can do is you can use smaller N size. So smaller N size give you larger capacity. Okay, so this is how sectoring is being used. So this is one, how you can improve the number of user per cell. You introduce sector. Okay, so it's just that problem with sector trunking channel, when you have number of user per sector is small. If you have one cell, you have 15 user. If you divide by 3, then you only have 5 and 5 and 5, 5 by 5. We know that having less number of user will give you trunking efficiency that is smaller. Okay, you need to start with a huge number of user. Okay, so these are just these advantages. I think I can read. So another part from sectoring is splitting. It is splitting. What is splitting? It's something like this. If we know here is 15 user, what if one size here is 15 frequency? If you want to have more user, what we can do? We can use a smaller cell. We build smaller cell. Then we get 15 times 7 over here. So you have 7 times of increment in the forms of user. So this is also one way. What does it mean? It means that you are using a smaller radius of the cell. So cell splitting. So initially was this big. Over 5 years, the number of user increase, then you have to reduce it to smaller. Okay, so you can, so instead of introducing sector, you can straight away reduce the cell size. Okay, so that is cell splitting. So you can, if you look from the cell splitting point of view, in one area, you can look something like this. So in the middle over here, maybe this is the city center. Okay, city center, the radius is going to be small. Okay, then once you go to the bigger one, then you can have a bigger cell. So this might be a residential. Okay, so from the point of view of planning, you can have also this kind of design, small, big, and big. So how you split your cell depending on how many user that you want to serve. More user, use smaller cell. Less crowded population, you can use a bigger cell. These are the two techniques, cell splitting and cell sectoring, that you can use to improve the number of users per cell. So advantages only need for cell that reach maximum. So if you only if the cell you can only do it for a cell that only on that reach maximum, meaning that you start with maybe 20, another 5 years, it is not sufficient anymore. Then you need to build a smaller cell within it. Okay, so you don't need to use to all cell. That is why in one area at the end it will look something like this. Okay, so there are area that is a very small cell, there are area bigger cell, there are areas even bigger cluster. Okay, so that is cell splitting. So again, this one no is hand off. What is later we will talk about hand off, because we allow mobility. We allow the mobility. The smaller the cell, the more hand off you have to deal with. The user may walk from one cell to another cell more often. Okay? So this one later, this how we deal with hand off. We're going to cover it later. Okay, so then another part that we do last week, how to increase the number of user. Once you know the number of user per cell, you can use trumping service to even increase the user. Okay, so that's, I think, finish. Any questions? Okay, so just wants to recap. So we look at interference. Okay, we look at the interference. We have co-channel interference, co-channel and adjacent channel. Okay, so this depend on D divided by R cube. Okay, so co-channel interference is depending on the on the reuse factor Q, or I can look at it as a quality, and it depends on the distance from the two co-channel cell and also the radius of the cell. The adjacent channel, the way to deal with it is channel assignment. Okay, to make sure that the adjacent channel is not going to be available in the same cell. Okay, 1, 2, 3, 4, 5. Okay, so you don't put 2 and 1 in the same cell. So cell splitting from big, you make sure it goes smaller. This is to increase the number of user. If you need to increase the number of user per area, when the population becoming bigger and bigger. Cell sectoring, you divide the cell into sector. It's either 120 or 60 degree divided by 6. Okay, that is cell sectoring. Okay, so these are the three topics that we gone through today. So with another one, by having sectoring, it improve S divided by I. Because of what? This number of interference reduces. Okay, reduces. 120, you only left with 2, 60 only 1. Initially, we start with 6. Okay, initially, there are 6 co-channel interference. Okay, when you start to use sectoring, when you only use the directional antenna, then some of the co-channel is not going to interfere with you anymore. Okay, then you reduce the number of interference. That increases your C over I. Increases C over I means that you can you can use a smaller cluster size. Okay, so these are the 3 topics that we do today. and hopefully, any questions before we stop? Okay, thank you so much. So if there are no questions, then tomorrow we'll meet back tomorrow as usual at 12. I'm planning to give you quiz maybe tomorrow. Okay, objective question, topic, question. Okay, with that, see you guys back tomorrow.